In electricity generation, an electric generator is a device that converts mechanical energy to electrical energy. A generator forces electric current to flow through an external circuit. The source of mechanical energy may be a reciprocating or turbine steam engine, water falling through a turbine or waterwheel, an internal combustion engine, a wind turbine, a hand crank, compressed air, or any other source of mechanical energy. Generators provide nearly all of the power for electric power grids. The reverse conversion of electrical energy into mechanical energy is done by an electric motor, and motors and generators have many similarities. Many motors can be mechanically driven to generate electricity and frequently make acceptable generators. History: before the connection between magnetism and electricity was discovered, electrostatic generators were used. They operated on electrostatic principles. Such generators generated very high voltage and low current. They operated by using moving electrically charged belts, plates, and discs that carried charge to a high potential electrode. The charge was generated using either of two mechanisms: electrostatic induction, the triboelectric effect, where the contact between two insulators leaves them charged. Because of their inefficiency and the difficulty of insulating machines that produced very high voltages, electrostatic generators had low power ratings, and were never used for generation of commercially significant quantities of electric power. The Wimshurst machine and Van der Graaf generator are examples of these machines that have survived. Theoretical development. The operating principle of electromagnetic generators was discovered in the years of 1831–1832 by Michael Faraday. The principle, later called Faraday's law, is that an electromotive force is generated in an electrical conductor which encircles a varying magnetic flux. He also built the first electromagnetic generator, called the Faraday disc, a type of homopolar generator, using a copper disc rotating between the poles of a horseshoe magnet. It produced a small DC voltage. This design was inefficient, due to self-canceling counterflows of current in regions that were not under the influence of the magnetic field. While current was induced directly underneath the magnet, the current would circulate backwards in regions that were outside the influence of the magnetic field. This counterflow limited the power output to the pickup wires, and induced waste heating of the copper disc. Later homopolar generators would solve this problem by using an array of magnets arranged around the disc perimeter to maintain a steady field effect in one current flow direction. Another disadvantage was that the output voltage was very low, due to the single current path through the magnetic flux. Experimenters found that using multiple turns of wire in a coil could produce higher, more useful voltages. Since the output voltage is proportional to the number of turns, generators could be easily designed to produce any desired voltage by varying the number of turns. Wire windings became a basic feature of all subsequent generator designs. Independently of Faraday, the Hungarian Enéas Jidlik started experimenting in 1827 with the electromagnetic rotating devices which he called electromagnetic self-rotors. In the prototype of the single-pole electric starter, both the stationary and the revolving parts were electromagnetic. He also may have formulated the concept of the dynamo in 1861 but didn't patent it as he thought he wasn't the first to realize this. Dynamo. The dynamo was the first electrical generator capable of delivering power for industry. The dynamo uses electromagnetic induction to convert mechanical rotation into direct current through the use of a commutator. An early dynamo was built by Hippolyte Picciel in 1832. The modern dynamo, fit for use in industrial applications, was invented independently by Sir Charles Wheatstone, Werner von Siemens and Samuel Alfred Varley. Varley took out a patent on December 24, 1866, while Siemens and Wheatstone both announced their discoveries on January 17, 1867, the latter delivering a paper on his discovery to the Royal Society. The dynamo electric machine employed self-powering electromagnetic field coils rather than permanent magnets to create the stator field. Wheatstone's design was similar to Siemens', with the difference that in the Siemens design the stator electromagnets were in series with the rotor, but in Wheatstone's design they were in parallel. the use of electromagnets rather than permanent magnets greatly increased the power output of a dynamo and enabled high-power generation for the first time. This invention led directly to the first major industrial uses of electricity. For example, in the 1870s Siemens used electromagnetic dynamos to power electric arc furnaces for the production of metals and other materials. The dynamo machine that was developed consisted of a stationary structure, which provides the magnetic field, and a set of rotating windings which turn within that field. On larger machines the constant magnetic field is provided by one or more electromagnets, which are usually called field coils. Alternating current generator. Through a series of discoveries, the dynamo became the source of many later inventions, especially the AC alternator, which was capable of generating alternating current, rather than direct current. Alternating current generating systems were known in simple forms for Michael Faraday's original discovery of the magnetic induction of electric current. Faraday himself built an early alternator. His machine was a rotating rectangle, whose operation was heteropolar. Each active conductor passed successively through regions where the magnetic field was in opposite directions. Large two-phase alternating current generators were built by a British electrician, J. H. Gordon, in 1882. The first public demonstration of an alternator system was given by William Stanley, Jr., an employee of Westinghouse Electric in 1886. Sebastian Ziani de Ferranti established Ferranti, Thomson and Inc. in 1882, to market his Ferranti-Thomson alternator, invented with the help of renowned physicist Lord Kelvin. His early alternators produced frequencies between 100 and 300 Hz. Ferranti went on to design the Deptford Power Station for the London Electric Supply Corporation in 1887 using an alternating current system. On its completion in 1891, it was the first truly modern power station, supplying high-voltage AC power that was then stepped down for consumer use on each street. This basic system remains in use today around the world. In 1891, Nikola Tesla patented a practical high-frequency alternator. After 1891, polyphase alternators were introduced to supply currents of multiple differing phases. Later alternators were designed for varying alternating current frequencies between 16 and about 100 Hz, for use with arc lighting, incandescent lighting and electric motors. Large power generation dynamos are now rarely seen due to the now nearly universal use of alternating current for power distribution. Before the adoption of AC, very large direct current dynamos were the only means of power generation and distribution. AC has come to dominate due to the ability of AC to be easily transformed to and from very high voltages to permit low losses over large distances. Electromagnetic generators, dynamo. A dynamo is an electrical generator that produces direct current with the use of a commutator. Dynamos were the first electrical generators capable of delivering power for industry, and the foundation upon which many other later electric power conversion devices were based, including the electric motor, the alternating current alternator, and the rotary converter. Today, the simpler alternator dominates large-scale power generation, for efficiency, reliability and cost reasons. A dynamo has the disadvantages of a mechanical commutator. Also, converting alternating to direct current using power rectification devices is effective and usually economic. Alternator. Without a commutator, a dynamo becomes an alternator, which is a synchronous singly fed generator. Alternators produce alternating current with a frequency that is based on the rotational speed of the rotor and the number of magnetic poles. Automotive alternators produce a varying frequency that changes with engine speed, which is then converted by a rectifier to DC. By comparison, alternators used to feed an electric power grid must operate at a speed determined by the frequency of the interconnecting grid. Some devices such as incandescent lamps and ballast-operated fluorescent lamps do not require a constant frequency, but synchronous motors such as an electric wall clocks do require a constant grid frequency. When attached to a larger electric grid with other alternators, an alternator will dynamically interact with the frequency already present on the grid, and operate at a speed that matches the grid frequency. If no driving power is applied, the alternator will continue to spin at a constant speed anyway, driven as a synchronous motor by the grid frequency. It is usually necessary for an alternator to be accelerated up to the correct speed and phase alignment before connecting to the grid, as any mismatch in frequency will cause the alternator to act as a synchronous motor, and suddenly leap to the correct phase alignment as it absorbs a large inrush current from the grid, which may damage the rotor and other equipment. Typical alternators use a rotating field winding excited with direct current, and a stationary winding that produces alternating current. Since the rotor field only requires a tiny fraction of the power generated by the machine, the brushes for the field contact can be relatively small. In the case of a brushless exciter, no brushes are used at all and the rotor shaft carries rectifiers to excite the main field winding. Induction generator. An induction generator or asynchronous generator is a type of AC electrical generator that uses the principles of induction motors to produce power. Induction generators operate by mechanically turning their rotor faster than the synchronous speed, giving negative slip. A regular AC asynchronous motor usually can be used as a generator, without any internal modifications. Induction generators are useful in applications such as mini hydropower plants, wind turbines, or in reducing high-pressure gas streams to lower pressure, because they can recover energy with relatively simple controls. To operate an induction generator must be excited with a leading voltage. This is usually done by connection to an electrical grid, or sometimes they are self-excited by using phase-correcting capacitors. MHD generator. A magneto-hydrodynamic generator directly extracts electric power from moving hot gases through a magnetic field, without the use of rotating electromagnetic machinery. MHD generators were originally developed because the output of a plasma MHD generator is a flame, well able to heat the boilers of a steam power plant. The first practical design was the AVCOMK25, developed in 1965. The U.S. government funded substantial development, culminating in a 25 MW demonstration plant in 1987. In the Soviet Union from 1972 until the late 1980s, the MHD plant U-25 was in regular commercial operation on the Moscow power system with a rating of 25 MW, the largest MHD plant rating in the world at the time. MHD generators operated as a topping cycle are currently less efficient than combined cycle gas turbines. Other rotating electromagnetic generators, other types of generators, such as the asynchronous or induction singly fed generator, the doubly fed generator, or the brushless wound rotor doubly fed generator, do not incorporate permanent magnets or field windings that establish a constant magnetic field, and as a result, are seeing success in variable speed constant frequency applications, such as wind turbines or other renewable energy technologies. The full output performance of any generator can be optimized with electronic control, but only the doubly fed generators or the brushless wound rotor doubly fed generator incorporate electronic control with power ratings that are substantially less than the power output of the generator under control, a feature which, by itself, offers cost, reliability and efficiency benefits. Homopolar generator. A homopolar generator is a DC electrical generator comprising an electrically conductive disc or cylinder rotating in a plane perpendicular to a uniform static magnetic field. A potential difference is created between the center of the disc and the rim, the electrical polarity depending on the direction of rotation and the orientation of the field. It is also known as a unipolar generator, a cyclic generator, disc dynamo, or Faraday disc. The voltage is typically low, on the order of a few volts in the case of small demonstration models, but large research generators can produce hundreds of volts, and some systems have multiple generators in series to produce an even larger voltage. They are unusual in that they can produce tremendous electric current, some more than 1,000,000 amperes, because the homopolar generator can be made to have very low internal resistance. Excitation. An electric generator or electric motor that uses field coils rather than permanent magnets requires a current to be present in the field coils for the device to be able to work. If the field coils are not powered, the rotor in a generator can spin without producing any usable electrical energy, while the rotor of a motor may not spin at all. Smaller generators are sometimes self-excited, which means the field coils are powered by the current produced by the generator itself. The field coils are connected in series or parallel with the armature winding. When the generator first starts to turn, the small amount of remnant magnetism present in the iron core provides a magnetic field to get it started, generating a small current in the armature. This flows through the field coils, creating a larger magnetic field which generates a larger armature current. This bootstrap process continues until the magnetic field in the core levels off due to saturation and the generator reaches a steady-state power output. Very large power station generators often utilize a separate smaller generator to excite the field coils of the larger. In the event of a severe widespread power outage where islanding of power stations has occurred, the stations may need to perform a black start to excite the fields of their largest generators, in order to restore customer power service. Electrostatic generator. An electrostatic generator, or electrostatic machine, is a mechanical device that produces static electricity, or electricity at high voltage and low continuous current. The knowledge of static electricity dates back to the earliest civilizations, but for millennia it remained merely an interesting and mystifying phenomenon, without a theory to explain its behavior and often confused with magnetism. By the end of the 17th century, researchers had developed practical means of generating electricity by friction, but the development of electrostatic machines did not begin in earnest until the 18th century, when they became fundamental instruments in the studies about the new science of electricity. Electrostatic generators operate by using manual power to transform mechanical work into electric energy. Electrostatic generators develop electrostatic charges of opposite signs rendered to two conductors, using only electric forces, and work by using moving plates, drums, or belts to carry electric charge to a high-potential electrode. The charge is generated by one of two methods, either the triboelectric effect or electrostatic induction. The Wimshurst influence machine was developed between 1880 and 1883 by British inventor James Wimshurst, as an electrostatic generator, a machine for generating high voltages. It has a distinctive appearance with two large contra-rotating discs mounted in a vertical plane, two crossed bars with metallic brushes, and a spark gap formed by two metal spheres. The van der Graaf generator was invented by American physicist Robert J. van der Graaf in 1929. It uses a moving belt to accumulate very high voltages on a hollow metal globe on the top of the stand. The potential difference achieved in modern van der Graaf generators can reach 5 megavolts. The van der Graaf generator can be thought of as a constant current source connected in parallel with a capacitor and a very large electrical resistance, so it can produce a visible electrical discharge to a nearby grounding surface which can potentially cause a spark depending on the voltage. Terminology. The two main parts of a generator or motor can be described in either mechanical or electrical terms. Mechanical, rotor, the rotating part of an electrical machine; stator, the stationary part of an electrical machine; electrical, armature, the power-producing component of an electrical machine. In a generator, alternator, or dynamo, the armature windings generate the electric current. The armature can be on either the rotor or the stator. Field, the magnetic field component of an electrical machine. The magnetic field of the dynamo or alternator can be provided by either electromagnets or permanent magnets mounted on either the rotor or the stator. Because power transferred into the field circuit is much less than in the armature circuit, AC generators nearly always have the field winding on the rotor and the stator as the armature winding. Only a small amount of field current must be transferred to the moving rotor, using slip rings. Direct current machines require a commutator on the rotating shaft to convert the alternating current produced by the armature to direct current, so the armature winding is on the rotor of the machine. Equivalent circuit. An equivalent circuit of a generator and load is shown in the diagram to the right. The generator is represented by an abstract generator consisting of an ideal voltage source and an internal resistance. The generators and parameters can be determined by measuring the winding resistance, and measuring the open circuit and loaded voltage for a defined current load. This is the simplest model of a generator. Further elements may need to be added for an accurate representation. In particular, inductance can be added to allow for the machine's windings and magnetic leakage flux, but a full representation can become much more complex than this. Specialized generators, vehicle-mounted generators. Early motor vehicles until about the 1960s tended to use DC generators with electromechanical regulators. These have now been replaced by alternators with built-in rectifier circuits, which are less costly and lighter for equivalent output. Moreover, the power output of a DC generator is proportional to rotational speed, whereas the power output of an alternator is independent of rotational speed. As a result, the charging output of an alternator at engine idle speed can be much greater than that of a DC generator. Automotive alternators power the electrical systems on the vehicle and recharge the battery after starting. Rated output will typically be in the range 50 to 100 A at 12 V, depending on the designed electrical load within the vehicle. Some cars now have electrically powered steering assistance and air conditioning, which places a high load on the electrical system. Large commercial vehicles are more likely to use 24 V to give sufficient power at the starter motor to turn over a large diesel engine. Vehicle alternators do not use permanent magnets and are typically only 50 to 60% efficient over a wide speed range. Motorcycle alternators often use permanent magnet stators made with rare earth magnets, since they can be made smaller and lighter than other types. See also hybrid vehicle. A magneto, like a dynamo, uses permanent magnets but generates alternating current like an alternator. Because of the limited field strength of permanent magnets, magneto generators are not used for high-power production applications, but have had specialist uses, particularly in lighthouses as they are simple and reliable. This reliability is part of why they're still used as ignition magnetos in aviation piston engines. Some of the smallest generators commonly found power bicycle lights. Called a bottle dynamo, these tend to be 0.5 ampere, permanent magnet alternators supplying 3 to 6 W at 6 V or 12 V being powered by the rider. Efficiency is at a premium, so these may incorporate rare earth magnets and are designed and manufactured with great precision. The maximum efficiency is around 80% for the best of these generators. 60% is more typical due in part to the rolling friction at the rear generator interface, imperfect alignment, the small size of the generator, and bearing losses. Cheaper designs tend to be less efficient. Due to the use of permanent magnets, efficiency falls at high speeds because the magnetic field strength cannot be controlled in any way. Hub dynamos remedy many of these flaws since they are internal to the bicycle hub and do not require an interface between the generator and tire. The increasing use of LED lights, more efficient than incandescent bulbs, reduces the power needed for cycle lighting. Sailing boats may use a water or wind power generator to trickle charge the batteries. A small propeller, wind turbine or impeller is connected to a low-power alternator and rectifier to supply currents of up to 12 A at typical cruising speeds. Still smaller generators are used in micropower applications. Engine generator. An engine generator is the combination of an electrical generator and an engine mounted together to form a single piece of self-contained equipment. The engines used are usually piston engines, but gas turbines can also be used. And there are even hybrid diesel-gas units, called dual-fuel units. Many different versions of engine generators are available, ranging from very small portable petrol-powered sets to large turbine installations. The primary advantage of engine generators is the ability to independently supply electricity, allowing the units to serve as backup power solutions. Human-powered electrical generators. A generator can also be driven by human muscle power. Human-powered direct current generators are commercially available, and have been the project of some DIY enthusiasts. Typically operated by means of pedal power, a converted bicycle trainer, or a foot pump, such generators can be practically used to charge batteries, and in some cases are designed with an integral inverter. The average adult could generate about 125 to 200 watts on a pedal-powered generator, but at a power of 200 W, A typical healthy human will reach complete exhaustion and fail to produce any more power after approximately 1.3 hours. Portable radio receivers with a crank are made to reduce battery purchase requirements, see clockwork radio. During the mid-20th century, pedal-powered radios were used throughout the Australian outback, to provide schooling, medical and other needs in remote stations and towns. Linear electric generator. In the simplest form of linear electric generator, a sliding magnet moves back and forth through a solenoid, a spool of copper wire. An alternating current is induced in the loops of wire by Faraday's law of induction each time the magnet slides through. This type of generator is used in the Faraday flashlight. Larger linear electricity generators are used in wave power schemes. Tate generator. A Tate generator is an electromechanical device which produces an output voltage proportional to its shaft speed. It may be used for a speed indicator or in a feedback speed control system. Two commonly used Tate generators are DC and AC Tate generators. Tate generators are frequently used to power tachometers to measure the speeds of electric motors, engines, and the equipment they power. Generators generate voltage roughly proportional to shaft speed. With precise construction and design, generators can be built to produce very precise voltages for certain ranges of shaft speeds. See also. References. External links, simple generator, demonstration of an electrical generator, short video of a simple generator.